Hi everybody. In this video we're going to talk a little bit about how satellites orbit the Earth, some of the terminology around that, and also some of the implications for either the spatial resolution or the temporal resolution with which satellites can collect imagery and get it down to us to use. So let's just start out with some basic orbital vocabulary, right? So here is the Earth. Okay, it's spinning on its axis. It's going this way. I guess you'd call that counterclockwise. And what do satellites do? Well, they do a number of things, but they orbit Earth, right? And so that means that they're always making a circle around Earth. That's all satellites can do, is basically trace a circle around Earth. And what really ends up defining their path and their characteristics is how big that circle is, and what the angle of that circle is, how it's tilted. So that's our first vocab word, will then be the inclination. So the inclination is the angle of a satellite's trajectory, an angle between the satellite track and the equator, essentially, where an inclination of 0 would be parallel to the equator. Okay? Another vocab I just mentioned would be the orbital radius, right? That's the radius of this circle that the satellite is tracing. And then we have the orbital period. That's the amount of time between orbits. Easiest way to think of that is how long does it take between when that orbit crosses the equator. That's a pretty common metric for satellites that are in a semi-polar orbit. And that's usually sometime around 90 minutes it takes to do a full circle around Earth and come back and cross the equator. So that's the orbital period. Okay, and the ground track is this dotted line. It is the line directly below the satellite. We care about that, of course, because that's what we're taking pictures of. So there's 3 end-member types of orbits. You can have any kind of orbit, but 3 that are common. One is the polar orbit, where you have a perfectly vertical orbit. You're crossing directly over the poles. Kind of a related version of that, or a similar version, is called the sun-synchronous orbit. So this is nearly polar. Maybe instead of having a 90 degree, it's a few degrees off of 90 degrees inclination. And it's designed, the sun-synchronous is designed so that the descending track of the orbit crosses the equator at the same local time every day. So a way to think about that is, if it takes 90 minutes to go around, then the Earth in that time has rotated kind of 90 minutes worth of time zone underneath the satellite as it goes around. And this is incredibly powerful for imaging, as we'll see in a bit. And then we have the geostationary orbit, which is an inclination of 0. Essentially, the orbit is going in the same plane as the equator. And to be geostationary, the satellite needs to make 1 revolution around Earth in the same amount of time that Earth itself does 1 revolution. So essentially, they're locked to each other. And the satellite, although yes, it is going around Earth, it's going at the same rate of rotation as Earth, so it's always pointing down at the same point on Earth. And that's why it's called geostationary. And by definition, it has an orbital period of 1 day. Okay, so hopefully you made notes on that. I just laid out a lot of stuff. Before we go any further, I want to show you an example of what orbits look like. So here's a pretty cool video that I will play. And what you can see, this really illustrates this idea that the satellite is always doing the same circle, right? And the Earth is simply spinning underneath it. And so in terms of imaging, we're really exploiting the rotation of the Earth to actually provide kind of fresh ground for the satellite to move over each time it comes back through. And if you want to have global coverage, the idea is to design your orbital period in a way that you get a lot of strips or tracks that get laid down next to each other without too much overlap. So this is why the orbit you're seeing in this video, kind of a subpolar orbit, maybe with a 88-degree inclination or something, is really the most common orbit because it does just that. It has a nice balance with the rotational velocity of the Earth to lay down a lot of parallel tracks over time. Okay, so I've mentioned this sun synchronous a couple of times. How about a real example? The best example or a common example is the Landsat satellites, 7 or 8. They've all had very, very similar orbits. So they have an orbital period of about 99 minutes. That means they go around Earth roughly 14 and a half times per day. That's a lot. And really important to note, they are placed in orbit such that they ascend on the dark side of Earth and they descend on the light side. So whenever you use a Landsat image, that is collected actually on the descent as this satellite comes from the poles back, the North Pole back towards the South Pole, and then it'll go back up in the dark side of the Earth. So here's an example of a geostationary orbit. These are very common for weather satellites. And the GOES mission has, I believe, multiple satellites that are orbiting at 36,000 kilometers, right? They're way far away from Earth. And we'll see in a second that's how far they have to be actually to only do one revolution per day. And because they're tagged to Earth, they're always staring down at the same spot on Earth. And of course, they have a pretty low spatial resolution. I don't know what the pixel size is, but maybe 10 kilometers or something. But the benefit is they can see a large area, and we can monitor weather systems over large scales in real time, getting continuous data. So when we think about how satellites get coverage of the globe, it's good to think about these traces in a map view. And so now we just have a flat map projection. Here's latitude, here's longitude. And so when you lay out Earth in this flat projection, you see that the satellite actually is tracing this kind of sigmoidal shape. And as it goes, as it repeats tracks and repeats its orbital periods, it lays down these tracks that have some step over relative to each other. And as I already mentioned, the orbital period and inclination will determine the repeat time of specific tracks. So most satellites are designed to lay down a bunch of tracks next to each other and then eventually repeat. So that repeat time could be anywhere from a day to weeks, or you could design orbits that actually would never repeat the exact same track. So a great example of this is, again, Landsat. Sorry, I'm always using it. But it's helpful to think about Landsat because here's a cool map that shows all 251 orbital paths or tracks. So here is, I think, track 250 is right about here. This is kind of track number 1. So it's not, the red lines are actually more dense. There's more tracks than are shown than red lines, but they give you an idea. 251 tracks, or we actually call them paths, descending paths. And then what's also good to know about Landsat and a lot of satellite data is it snaps photographs or compiles data at very regular intervals as well. So as the satellite is descending down through here, there are, I don't know how many rows, I think 140 or 180 rows that are predetermined, right? So essentially what ends up happening is the globe is gridded out into a bunch of, blocks that are defined by the satellite, the descending path, as well as the row or the latitude in which that photograph was snapped. So when you look for images, you'll often see them listed or cataloged by path and row. Okay, so I want to move towards the end of this video by talking about kind of what controls the orbital period and thus the kind of repeat time and also the spatial resolution of satellites. So the number of orbits per day is defined by the velocity of the satellite and the height at which the satellite is flying. And it turns out these two things are totally related. They're codependent. And the reason for that is that essentially to stay in orbit, the satellite has to be going a certain speed. And the speed that it needs to go to stay in orbit is the speed that balances gravitational force against centrifugal force. Okay? So gravitational force here is given by mass times the grav constant times Earth radius divided by orbital radius. So that's the force pulling the satellite down towards Earth. The force pulling it away or counterbalancing that is the centrifugal force. That is given by the mass times velocity squared divided by the orbital radius. So if we set these two equal to each other, a perfect force balance that will keep the satellite flying instead of crashing back to Earth, we can then solve that for velocity. And we see that there's this trade-off where if you were to increase the orbital radius, in other words, fly the satellite higher, you would have to slow the satellite down. Velocity gets lower. Okay, and so this kind of encapsulates the key relationship that low satellites need to fly faster. And so what do we mean by this? And I'm actually going to ask you to do this as a homework problem. What is the velocity of a satellite at 700 kilometers, which is a common orbital height? It is 7,500 meters per second, 7.5 kilometers per second. These satellites are smoking fast. So summary of that, the lower a satellite flies, the faster it must go, okay? And if you have a faster, lower satellite, okay, that means it's going to do more orbits per day. It's going to have a much shorter orbital period. It's going to be, doing 17 laps per day instead of 14 laps around Earth per day. And so it turns out we can consolidate these relationships into this graph, which is complicated, but it kind of has all the important stuff on it. What it shows is that if you fly a satellite at a unique altitude, say 400 kilometers, 600, or 800 kilometers, that actually defines a very specific velocity, right? And then the combination of the velocity and the height define a very specific period. So we could use a figure like this to ask, what would the velocity and period be for Landsat 7 flying at 715 kilometer elevation? So it would have a period of somewhere between 1.5 and 2 hours. So just to summarize that again, if you put a satellite higher in orbit, you're going to get a large field of view, typically because you're looking down from higher, and you may get a shorter repeat time because of that larger field of view, but you're going to get low spatial resolution. Okay, if the satellite flies low, you may get higher spatial resolution because you're closer to Earth, but you'll often would have a longer repeat time and perhaps a narrower field of view. So in summary, we talked about 3 orbits: polar, sun-synchronous, and geostationary. We talked about how the orbital period, the inclination, and the rotation of Earth determine the repeat time, or when an exact track might be repeated. We showed that lower satellites must fly faster and have a shorter period. And if you assume those lower satellites have a smaller field of view, then that would give you often a longer repeat time, even though they might be flying a bit faster. Thanks, everybody.